Thank you very much, Chairman. And I'd also thank for organizers for giving me a chance to talk about my recent works in these beautiful islands. The title of my talk is Ultrafast anisotropic polarization dynamics in the electronic ferroelectrics. So my name is Yoichi Okimoto from the Tokyo Institute of Technology. And they are my collaborators. Especially most of these works were done by Dr. Hong Wu, my student in Tokyo Institute of Technology. And also, all the samples, single crystals, were fabricated by the Professor Ikeda's group in Okayama University. And as for the terahertz measurements, I collaborated with Hirotake and Shinichiro. Yes, I really thank them all. Today's my topic is ferroelectrics. So first, all of you know the ferroelectrics well, but the ferroelectrics has two important key features to understanding it. One is a polar structure driven by the breaking of the inversion symmetry, and the second one is more important: polarization reversal by electric field. Those two features are quite interesting. And taking advantage of those two features, the ferroelectrics are applied to various fields in our daily life, such as random access memory, mechanical actuator, and capacitance, and so on. So it is quite important for us to develop or study the exotic ferroelectrics in addition to the usual conventional ferroelectrics. Is quite important. Okay. So I chose, so there are several important exotic ferroelectrics in the world. So among such many candidates of the exotic ferroelectrics, I chose so-called electronic ferroelectrics as my research target. That first, I'd like to talk about the electronic ferroelectrics. Then what's the electronic ferroelectrics? So in these materials, so the electron ordering, not a cation or anion ordering, causes the polarization in the materials. Here's an example of the one-dimensional iron crystal composed of Fe2 plus and Fe3 plus. If the electrons are itinerant, so that you can see no polarization, because all the iron cations takes 2.5 plus. However, some ordering of the Fe3 plus and Fe2 plus occurs. So you can see arrangement of the P, polarization. Then the polarization occurs by the order of the electrons without shift of any ions. This is a typical schematics to explain the electronic ferroelectrics. Of course, in the electronic ferroelectrics, the role of electron correlation is quite important, as Professor Ishihara proposed in 2010. The next point is, what's the merit, important merit of the electronic ferroelectrics? So in this electronic ferroelectrics, electron can play an important role rather than the ion or atoms. So the electrons are even lighter than the atoms, so that we can easily change the polarization with a lower voltage and with ultra-fast response. So those are the merits of the electronic ferroelectrics. So based on these respects, so several candidates for the electronic ferroelectrics has been proposed in organic crystals, TM-TTF2X, alphabet TTF2I3, and 205, the Professor Ikeda proposed the lutetium RFe204 as the electronic ferroelectrics. So today, I'd like to talk about these materials. First, I would like to make a brief introduction of the lutetium RFe204 proposed by the Professor Ikeda in 2005. The average valence of the iron is 2.5. So this means the Fe2 plus and Fe3 plus are 1 to 1. Okay. So here is the crystal structure of these crystals. So the green circle is the layers. This layer is called the layers layer. And the point is that this double sheets composed of the iron iron and oxygen. So that this is called the double layer. So that we expand this double layer here. So the green, red circle is Fe3 plus, and blue circle is Fe2 plus. So that the double layer is composed of the two sheets. And in the upper sheet, so that you can see the Fe3 plus is rich. And in the lower layer, the Fe2 plus is rich. So that you can see the existence of the polarization along this direction. So this is the scenario of the electronic polarization in these materials. But after his proposal, more than 10 years, more than 14 years, there was many controversy. One of the reasons is that there was scarce good single crystal at the time. And also, so the second reason is neutron diffraction measurements couldn't determine the crystal symmetry, let alone the polarization. So the neutron diffraction measurements suggest the three candidates, C2, Cm, and C2 over M, polar, polar, and nonpolar. So after this proposal, so for more than 14 years, so there are many struggles. To solve these problems, we measured the second harmonic generation in the lutetium Fe204 and ytterbium Fe204. So very fortunately, so that I could detect the SH signal from this ferroelectric materials. The left panel shows the azimuth angle dependence of the SHG polarized along the A-axis. The right panel shows the azimuth angle dependence of SHG polarized along the BM axis. In both data, you can see a clear four leaves angle dependence. So the first message is here, so that we could safely observe the SHG. So that this indicates the material, this lutetium Fe204 or ytterbium Fe204 has a polar structure. A point is a strong femtosecond laser pulse is indispensable to observe the SHG of this material. In other words, the SHG signal from this material is too weak. So we try to measure the SHG signal using the nanosecond laser pulse, but in vain. Okay, so the next problem is how do we understand this angle dependence? This is the angle dependence, azimuth angle dependence of the SHG in the lutetium Fe204. The angle profile is almost the same as the ytterbium Fe204. To understand this angle dependence, so that we assume the monoclinic Cm, which is one of the candidate based on the neutron diffraction measurements. And according to the international table, so that we can easily see the contracted Chi2 tensor like this for this symmetry. By using this tensor components, the SHG polarized along the A-axis is described by this one. And SHG polarized along the B-axis is described by this one. So that by using this formula, this angle profile well fit. So we succeeded in concluding the polarization structure of this material is Cm, in which the polarization exists in AC plane. This is first conclusion. Okay, so let's go on to the second part. The second part, so that we checked the polarization, the existence of the polarization of this system. The next problem is whether the polarization can be reversed or not. That is a quite important problem in the ferroelectrics. But unfortunately, this lutetium Fe204 is a little bit conductive, so that we can't use the conventional measure system for the usual ferroelectric materials, such as the P loop measurement. So that we considered, based on the SHG measurements, so that we measured such a polarization reversal. So here is the experiment setup. So you can see sample here, crystal here. So we fabricate some electrodes by a silver paste. So that we apply the electric field by this source meter. With applying the electric field, we irradiate the crystal with a 800 nanometer pulse. After that, so we detected the generated SHG pulse of 400 nanometer using the appropriate filter, monochrometer, and photomultipliers. Okay, so I will show you the results. Relative electric field dependence of relative change of the SHG. So the SHG is plotted at this point. This is a D11 component, the most strong one, strong SHG point. Let's start from here. As the electric field is applied, the polarization in the crystal is aligned, and the SHG value increases from here to the blue circles. When the electric field is reversed, a reentrant variation is observed at around the 10 volt per centimeter, 10 volt centimeter, like this. And finally, so that with decreasing the electric field, the change of the SHG is kept from here to here. Okay. So this electric field dependence of the SHG is a little bit complicated, but scenario is quite simple. The left panel shows the P loop in usual ferroelectric materials in the textbook. However, so that if we monitor this P loop by using the SHG, then what happened? The SHG is proportional to the P squared. So the electric field dependence of the SHG is written like this. At first, so the SHG increases, polarization increases, and with decreasing the electric field, the domain reversal occurs. Then, SHG shows such a reentrant behavior from here. So the observed reentrant behavior in the SHG is a strong evidence of the reversal of the polarized domains. And in addition to the conclusion, so another important point is such a coercive electric field. The polarization can be reversed with a field of less than 10 volt per square centimeter, 10 volt per centimeter. This deep point, the electric field at the deep point is about 10 volt per centimeter. So for example, so in PZT is a famous conventional ferroelectrics, lead titanate. The coercive electric field is about 1 kilovolt per centimeter. So the coercive electric field is even smaller than the case of the usual ferroelectrics. That's the second message of these materials. Okay, so now that we revealed the lutetium Fe204 or yttrium Fe204 are ferroelectrics. So we try to observe the ultrafast response of the electronic ferroelectric materials. Okay, so we performed the pump and probe SHG measurements using the 35 femtosecond pulses. Here is the experiment setup. So for the pump light, so that we chose the 800 nanometer pulse. So that this excites the dB transition between the iron sides, and this disturbs the charge ordering of the iron side, AB plane. So we investigated what happens in the SHG with the destruction of the iron order. Here is the experiment setup. So that we irradiate the 800 nanometer light to the crystals, okay, burn. After that, so that we irradiate the crystal with a 1300 nanometer probe light, and we detect the SHG light of the 650 nanometer by using the filter, monochrometer, and photomultipliers. Now, before showing the pump and probe data, I will show you the in-plane and out-of-plane optical conductivity of these materials. So in both polarizations, you can see a broad peak at around the 1.5 eV, 800 nanometer. And also so that you can see a huge absorption above the 3 eV. So the former is assigned a DD transition between the Fe2 plus to the Fe3 plus DD transition. And the second one is assigned as the CT transition, charge transfer excitation, oxygen 2p to the Fe3b sites. So as I told you, so that we chose this 1.5 eV, 800 nanometer light as a pump light. So the pump light can excite the iron TT transition. Okay, I will show you the pump and probe data. So this is a relative change, time dependence of the relative change of SHG in this point, D11 point. Okay, so with excitation, just after the photo excitation, you can see a huge drop of the relative change of the SHG intensity down to 30%. So this indicates the instant suppression of the polarity of these materials. After that, so you can see a slight relaxation, and long-lived flat state. So by using this formula, and also considering the pulse width of the laser light, so that we extract the decay time. First decay time, 0.12 picosecond, and second decay time is about 0.3 picosecond. So anyway, we observe the huge suppression of the D11 component in SHG. So this indicates a disorder of the charge order in the AV plane. But this is a quite reasonable conclusion we had expected. The important result is this dynamics along the C-axis. By using AC plane, so we measured the time dependence of the relative change of the SHG along C-axis. So just after photo irradiations, the C-axis polarized SHG show a small drop. However, after that, the SHG increases from here to here by 8%. And after that, so such an increase gradually decreased from here to here. So we observe the enhancement of the SHG along the axis. By using this data and the previous data, so we extracted the tensor component at selected delay times denoted by those triangles. So this is the time dependence of the tensor component of D11, D33, and D35. The D11 component is a disorder of the polarization in the AV plane, and the D33 component corresponds to the C-axis polarization. So the D11 component is still decreased. However, the D33 component is increased by the photo excitation. So this is the point. Enhancement of the D33. This indicates an increase of the polarization, nonlinear polarization along the C-axis. This is the second conclusion. This is summary of the anisotropic polarization of the lutetium RFe204. This is the ground state. So we irradiate the 800 nanometer pulse. Then, at first, so we observed this one. So in the first stage, the charge order in the W layer is largely perturbed. So this is a decrease of the SHG along the AV plane. However, the charge disproportionation along the C-axis is kept, preserved. So this is the reason why the C-axis component is not so changed. Second, so we observed the instant enhancement of SHG along the C-axis, keeping the disorder in the AV plane. As for the origin of the second this stage, we cannot conclude a definite scenario. We cannot say a definite scenario, but we can consider that those two reasons. So one is the photonic structural change by the photo excitations. So some photo excitation, some structural change occurs by the photo excitation. So that's the resultant increase of the chi2 of these materials. The second origin is some increase of the correlation length of the charge disproportionation. Actually, according to the neutron diffraction measurements, the correlation length of the double layer along the C-axis is not so large, about 5 unit or so. After the photo irradiation, such a correlation length, if the correlation length increases, then the SHG along the C-axis can increase. At the present stage, so that, we cannot conclude which is which. But I'm trying to measure the ultrafast femtosecond X-ray diffraction measurements in these materials. And finally, so that we observe the long-lived state in plane disordered, but charge disproportionation is preserved. And this is the anisotropic dynamics of the lutetium Fe204. So finally, I will show you the terahertz response of the ytterbium Fe204. So we perform the pump and probe SHG measurement using a 100 femtosecond terahertz pulse. So in general, terahertz pulse has locked field oscillation and can be viewed as the oscillating strong electric field. So by applying such a strong electric field, so that we observed what happens. So such a type of experiment has been done in various ferroelectrics like this, including my work. So here is the experimental setup for the pump and probe SHG measurement using the 100 femtosecond terahertz pulse. So we irradiate the pump pulse, namely the terahertz pulse, by using the parabolic mirror to the samples. Okay, and with that, so that we irradiate the 800 nanometer pulse through the parabolic mirror to the samples, and we detected the generated SHG by using the filter, monochrometer, and photomultipliers. Then, how about the electronic ferroelectrics in the pump and probe SHG measurement? For the pump and probe terahertz spectroscopy measurements, so that I collaborated with the Iwai group in Tohoku University. So this panel shows the applied electric field waveform. The maximum value of the terahertz field is about 200 kilovolt per centimeter, about 200. So that we apply the electric field along the b-axis, perpendicular to the polarization, perpendicular pole. So this is the angle dependence of the SHG before the photoexcitation, as I told you. This is, you can see a four leaves type azimuth angle dependence. However, if we apply this terahertz field to this one, along this b-axis, then we observe the huge change of the angle dependence of the SHG. And along this direction, so the SHG magnitude increased by more than 170%. This is the largest value as far as I know in the case of the ferroelectric materials. Why did we observe such asymmetric angle dependence in the lutetium Fe204 or ytterbium Fe204? This is a unit cell of the CM unit cell of this material with these crystals. And we apply the electric field along this direction, b-axis, along this direction. If we apply strong electric field to the systems, the crystal symmetry is changed from the monoclinic structure, original monoclinic structure, to the triclinic structure. So by applying electric field, so that we observed the triclinically distorted systems. So that is the reason why we observed such a asymmetric shape of the azimuth angle dependence. Finally, so that I will show you the time dependence of the azimuth angle dependence of these crystals, ytterbium Fe204. So at this point, so that we observe this one, this is the largest change. So you can see the asymmetric change of the SHG, or angle dependence of the SHG, almost follows the terahertz waveform, like this one. So we can conclude that this electronic ferroelectric material shows the ultra-fast large change of the direction of P, as well as the magnitude of the polarization. This is the conclusion. Okay, so this is the summary. So my work can be summarized by this sentence. The RFe204 shows the electronic ferroelectricity at room temperature with energy saving and ultra-fast polarization variations. So based on those features, so now, so the research network is expanding around me. So in this conference, so if you are interested in these materials, so I'd like to collaborate. I would like to some collaborations. So now, so that we intend to strive to replace ordinary ferroelectrics with such electronic ferroelectric iron materials. Thank you very much for your attention.